Graphing inequalities in slope-intercept form. Remember that the slope-intercept form of a line is just y equals mx plus b, and in this case this is an equation because it has an equal sign. Well, today we're going to be graphing inequalities, and we're going to be using some of the same skills that we already know for graphing equations. So if you don't remember how to do that, I would encourage you to go back and find the video on graphing lines in slope-intercept form. Okay, so let's look at these examples right here. We have y is greater than 1/3 x minus 2, and then we have our second example is y is less than or equal to negative 2/5 x plus 2. Now I've gone ahead and taken some points. I've acted as though this were actually an equation and plotted some points that would fall on that line. Okay, I've done that for both examples here. Now we do still need to connect these points with the line, but what type of line we use depends on what kind of inequality symbol we have. So this first one right here, it says y is greater than. Anytime you have a greater than or a less than symbol, you are going to use a dashed or a dotted line. Okay, so we're going to connect these points, but we're going to do so with this dashed line. All right. Now, that's kind of like our boundary line. Now, what this inequality says is we want all of the points that have y values that are greater than this expression right here. Y values are greater than the expression. So think for a minute, are the y values above the line greater or the y values below the line greater? And hopefully intuitively you just know by definition, greater than, we would want the values that are above the line. So we are going to shade the entire region above our inequality. Okay, so that means every single point that sits above this boundary line is a solution. It will make this inequality right here true. Okay, so let's do a test point. That is how we can solve our problem graphically, but we can also use points like this algebraically. So let's test the point 0, 0, our origin. Okay, if I were to take the x value of 0 and substitute it into the inequality, and the y value of 0 and sub it in, my inequality should still be true. So let's try that. 0 should be greater than 1/3, and instead of x, we'll sub in the 0 minus 2. Let's simplify that. 1/3 times 0 is definitely 0, so this gives us 0 is greater than negative 2. Now, is that true or false? It's definitely true. That is why the origin is a solution. Okay, so any point that falls in that region is true. And don't forget, we have limited resources, right? We don't have paper that extends forever in all directions or a computer screen. But theoretically, this coordinate plane extends left and right and up and down forever, okay? So any point that sits above this dashed line is going to be a solution. But what about a point that actually falls on the dashed line? For example, this point right here that's located at 6, 0. Should I include the points that actually fall on that dashed boundary line? Well, let's try it out and see. Instead of our x value, we're going to sub in the value of 6, and for the y value, we'll sub in a 0 again. Okay, so let's try that out. 0 should be greater than 1/3 times 6 minus 2. Well, what is 1/3 times 6? 1/3 times 6 is just 2. So 0 should be greater than 2 minus 2. But 2 minus 2 is actually 0. Does it make sense for us to say that 0 is greater than 0? That's definitely false. That is why we do not include values that fall on our dashed boundary line. This point right here is not a solution, okay? Now let's look at our second example. It says y is less than or equal to negative 2/5 x plus 2. In this instance, we have our less than or equal to symbol, but we also could have had a greater than or equal to symbol. Anytime you have your inequality with this or equal to symbol, we are going to graph a solid line. It's not dashed anymore, it's solid. Okay? Now, which direction should we say? If this says y is less than or equal to, and hopefully you recognize that all of the values, the y values less than, would go below the line. So let's go ahead and shade everything below the line this time. All right, and now we want to, we can check our test points. Let me do an example of a value that's not in the shaded region. If we were to test the point, let's say 6, 0, this one right here. I'm sorry, 0, 6. X always goes first. I'm so silly. All right, so my X value is 0, and my Y value would be a 6. So let's sub those values in. 6 should be less than or equal to -2/5 times 0 plus 2. Well, let's see. -2/5 times 0 is definitely 0. And then this says 6 is less than or equal to 2. Is that true or false? It's definitely false, which is why this point is not in the shaded region. It is not a solution to our inequality. It makes our inequality false. So that's an example of why the shaded region does not give us solutions. But what about values that actually fall on our boundary? So let's do this one right here. We have the point 5, 0. 5, 0. So this time we're going to substitute in the number 5 for our X value and 0 for our Y value. Okay, so 0 should be less than or equal to -2/5 times our X value of 5 plus 2. All right, -2/5 times 5. When we multiply those together, the 5's reduce, and we're left with -2 plus 2. So 0 is less than or equal to -2 plus 2. Well, -2 plus 2 is just 0, so 0 should be less than or equal to 0. And that's definitely true because of this or equal to symbol right here. So this point is a solution. This point is a solution. So in this instance, when we have a point that actually falls on a solid boundary line, that will represent a solution. So we've come up with 2 ways of determining solutions or points that make our inequality true. We can either graph and shade the regions, or you can actually use test points and sub those into your inequalities and see algebraically if those values make your inequality true or false. Now in the next video, we'll talk about graphing inequalities in standard form.